Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on the 26th of June 2025, T 17 hours 59 minutes and 14 seconds .0000Z. This paper, published just 2 days ago, introduces an automated data engine that can generate training labels orders of magnitude faster than human annotation. The paper is titled SAM4D, Segment Anything in Camera and LiDAR Streams, and this new approach could dramatically cut down on the huge data costs for autonomous driving. The authors present a foundation model that understands and segments objects using prompts in both camera images and LiDAR point clouds simultaneously. Also, the authors shared their official GitHub repository for SAM4D. If you head over there, you'll find a detailed README that gives a great overview of the project and their method. It covers their approach for aligning camera and LiDAR streams, along with links to the paper and project page. Okay, so this first figure really lays out their entire three-part contribution. First, it shows the core task. You can prompt the model in one view, say with a box on a car in a camera image, and it segments that car in both the video and the corresponding LiDAR stream. LiDAR, by the way, is the laser-based system that creates a 3D map. The second part shows the SAM4D model itself, which uses a key component called Unified Multi-modal Positional Encoding, or UMPE, to align the 2D and 3D data. Finally, it details the automated data engine that generated their massive Waymo 4D seg dataset. So, digging into the model itself, this diagram shows the full SAM4D workflow. It starts with two data streams, camera, video, and LiDAR scans, which are processed by separate encoders. The magic really begins with that Unified Multi-modal Positional Encoding we mentioned, which projects everything into a shared 3D space. Then, a component called Motion-Aware Cross-modal Memory Attention, or MCMA, uses the car's own movement to help track objects consistently over time. This enhanced data is then used by a decoder to create the final, precise segmentations. Alright, so we've seen how the model itself works, but where does it get its massive amount of training data? This diagram details the automated data engine that creates it. First, it generates what it calls masklets from video, which are basically small, specific segmentation masks for objects. At the same time, it reconstructs a 4D scene from the LiDAR data using voxels, which you can think of as 3D pixels. Finally, it fuses these 2D video masklets with the 3D voxels, creating high-quality, automatically generated labels or pseudo-labels for the model to train on. So with that massive dataset in hand, how well does the model actually perform? This first table compares performance using different kinds of prompts for this cross-modal task. The main metric here is mean intersection over union, or MIOU, which basically measures how much the model's predicted segmentation overlaps with the correct one. And what's really interesting is that prompting in one modality works well for the other. For example, giving 3 simple clicks on an image results in a LiDAR MIOU of 53.1%, showing this cross-modal alignment is really effective. Building on those results, these next tables show 2 ablation studies, which are where researchers test how important each part of the model is. The first table shows that the full SAM4D model, using both camera and LiDAR, clearly outperforms versions using only one data source. It gets the highest mean intersection over union and the lowest number of mismatched points, which counts tracking errors. The second table then shows that using higher resolution inputs also boosts performance significantly across the board. This all confirms their design choices are really effective. This final ablation study then zooms in on one specific but critical component, ego motion. That's the car's own movement. This table compares the model's performance with and without compensating for that movement in its memory. The results are really clear. When the model accounts for ego motion, the LiDAR segmentation gets a big boost. Its mean intersection over union jumps by over 3%, and the number of mismatched points, those tracking errors, drops dramatically from 746 to 582. This really proves how vital that motion-aware cross-modal memory attention is for temporal consistency. So to wrap things up on SAM4D, we've seen a model that truly advances 4D scene understanding for autonomous driving. The key takeaway is how its innovative architecture, especially that motion-aware cross-modal memory attention, uses the car's own movement to create incredibly consistent object tracking over time. This approach, combined with its automated data engine for generating labels, not only boosts performance, but also tackles a huge real-world problem, the high cost of data annotation. It's a powerful step towards more robust and adaptable perception systems. That's all for this paper. Thanks for tuning in.